The half-life of radioactive element potassium-42 is 12.4 hours. This element is commonly used in biology experiments because of its short half-life. Suppose we have a 2-gram sample. So we know this is an exponential situation because it's a half-life problem. And remember, that means that the half-life is the amount of time it takes for the quantity to decay to half of its original size. So you'd be multiplying by 1/2 to get the amount after 12.4 hours. So we have two quantities that are changing. We have the amount of time. So time is measured in hours. And then we have the amount of potassium, and it looks like that is measured in grams. So we'll let Y be the number of grams. And because this is an exponential relationship, we can use our general exponential equation, y equals y sub 0 e raised to the kt power. And I recommend organizing the information in the table, organizing the information in the problem in a table. So at times 0, how many grams of potassium do we have? And the problem states we have 2. Then the only other information given to us is this amount of time, 12.4. So 12.4 is a time, and that's the half-life. Again, that's how much time it takes for our 2-gram sample to decay to half as much. So half of 2 would be 1. And now we have enough basic information to begin solving for the unknowns in our problem. And remember, we have two unknowns, y sub 0, which is the initial amount, and our value for k. K is our relative decay rate. So we know y sub 0 because we know that there were initially 2 grams of potassium. So we can substitute 2 in for y sub 0. And then we can use the 12.4 and the 1. Think of this as an ordered pair. And we can substitute these values in for t and y. So when y is 1, t is 12.4. And occasionally I have seen a couple students make the mistake and write these values in the wrong places because we're so used to having a y value over here that is larger. But because this is a half-life situation, that's not the case. So just make sure you look at your variables carefully. Again, that's the benefit of using a table. So now we're going to solve for k. Dividing by 2 first. And this is an exponential equation. So now we'll write this equation in log form. The base of the logarithm being e. So log base e is natural log. Natural log of 0.5 equals k times 12.4. Therefore, k equals the natural log of 0.5 divided by 12.4. So this is the exact value for k. And then I would recommend that you go to your calculator to check out the decimal form. So if you put that in your calculator, it looks like k is approximately negative 0.056, which makes sense that this is a negative value because this is a decay situation. Now, we don't actually want to use the decimal for any of our future computations because this is a rounded decimal, so we don't want to lose accuracy. So I want you to go ahead and practice storing that decimal on your calculator. So a quick review of that. Remember, the store button is in the lower left corner. It's above the on key. It says STO, stands for store. So hit your store button. And when you do that, you'll see ANS arrow on your screen, which means we're going to store this answer as any letter we want. And so you can choose X if you want. You can choose K if you'd like. If you want to use K, then you'll use the alpha button on your calculator. You can choose any letter you want and then press enter. And this is going to store that decimal as whatever letter you've chosen. So I'm choosing K. And now we're ready to actually answer part A of this problem. So part A says how much will be remaining after t hours, meaning it wants us to write an equation in terms of t for this decay. And we have our basic equation right here, y equals 2e to the kt. And now that we have k, we can go ahead and substitute that in. So our model is y equals 2e raised to the negative 0.056 t power. part B. When will there be 0.7 grams remaining? So we've been given the value of 0.7, and we just have to decide whether that is a t or a y value. And because it's measured in grams, that's a y value. So we're going to substitute 0.7 in for the y value of our equation, and we're solving for time. So same exact process that we just used to solve for k, only now we're solving for time when y equals 0.7. So divide both sides by 2. 0.35 equals e raised to the negative 0.056t. Rewrite your equation in log form, and then divide. However, when you go to do this division step, although I'm writing that we're dividing by negative 0.056, we're not actually going to divide by that. We're going to use our stored value here. So if you stored your relative decay rate as k, then you'll divide by k, or divide by x if you stored it as x. So make sure you try all of these calculations on your calculator so that you're not making any sort of calculator mistake. And it looks like this should come out to about 18.78. And this is a time, so that would be 18.78 hours. And I always recommend that you check to see if this would be a feasible answer. So going back to your table, if the half-life is 12.4, then we could have another 12.4 hours elapse. So that would take us to 24.8 hours. And that means I would have half of what I had previously, and that would be then 0.5 grams. And if you think about that for a second, this part of the problem, part B, wanted to know when we would have 0.7 grams. So 0.7 grams would lie here in between 1 and 0.5. Therefore, we expect our time to be something between 12.4 and 24.8. So our answer of 18.78 makes sense. Part C. How fast is the mass decaying after 6 hours? So you'll notice in the problem so far, we haven't done any calculus. Finally, we get to do a little calculus here because it's asking for how fast this mass is decaying. So it's looking for a rate of change. So we can compute that by finding our derivative, and we want our derivative at 6 hours. So that's what we're looking for here. Therefore, we need to find the derivative of the function that we wrote in part A, which is exponential. So since it is exponential, notice also it's a composite function. So we have an outer function of 2e raised to the something power and an inner function of negative 0.056t. So the derivative of the outer will be 2e to the something. Then we'll substitute in our g function. And then we need to multiply, this is the chain rule part, we're multiplying by the derivative of g, which will be negative 0.056. Once again, noting that I'm not going to actually type that decimal, I'm going to use the stored value in both of these places. So now using your calculator, we're going to substitute in 6. And I'll ask you to round to 2 decimals on all of your computations here, just so I can check the accuracy of your computations, making sure that you didn't round multiple times in the problem, but rather that you just round one time at the very, very end. And this looks to come out to about negative 0.08. Again, this makes sense since this is a rate of change and it's negative because this is a decay situation. Think graphically for just a second what exponential decay would look like graphically. So we expect to have a negative slope everywhere on that curve. And then you want to make sure that you attach units. So because this is the derivative, remember this is not the amount of potassium, but rather how fast the mass is decaying. So think of it as the change in y over the change in t. Y is measured in grams, and t is measured in hours. So this would be negative 0.08 grams per hour.